Okay, so what we've just done is we've just gone ahead and defined a continuous time concept of impulse. Okay, so now that we've done this, we have kind of all the tools we need to motivate the continuous time impulse response map. Okay, so this is our next goal. So our next goal is to study the continuous time impulse response map. Okay? Now, like I said earlier, what we're going to do is we're going to use the discrete time case as a template for our study in the continuous time case. Okay? So let's think back to how we defined our impulse response map in the discrete time case. Well, what you might remember is that Hij, right? Or let me draw this with little brackets just to make myself extra clear. Hij in the discrete time case was the response of output coordinate I to an impulse applied in input coordinate j. Okay? So this was the basic idea that we had in discrete time, right? This is what our impulse response map kind of should be defined as, all right? So again, using this discrete time case as a template, we'll just translate this idea directly over to continuous time, okay? So in order to kind of figure out what a nice expression for the continuous time impulse response map should be, we'll just kind of work out using our very informal integral rules, which, remember, you should just think of as notation, right, to kind of convey what a convolution with a distribution is doing. We're going to use these rules to work out what a formula for continuous time impulse response might be. Okay? So what I'm going to do now is I'm going to look for a continuous time response to an input u equals now a continuous time delta as a function of time. Okay, remember, this is not actually true. This is not what a delta truly is. We're just using it for the sake of exposition here. Okay, so delta times ej to make sure that this shows up in the jth coordinate of our input. Okay, and I'll just go ahead and I will use the formula for the IO map, or excuse me, the zero state response that we kind of derived in previous lectures. So you might remember we have rho of t, t naught, 0, u equals c of t times the integral from t naught until t, phi of t, tau, b of tau, u of tau, d tau, plus d of t, u of t, right? So if I just go ahead and I plug in this delta ej, what do I end up getting? Well, I get that this guy is equal to c of t, integral from t naught up until t, of phi of t tau, b of tau, times ej, times delta of tau, remember, just notation, right? D tau, plus d of t delta of t, okay? And actually, what I'm going to want to do here is I'm actually going to want to use a shifted delta. Excuse me. So this should be at t naught. This should be at t naught. Okay? And remember, our reasoning for that was this impulse response map should start at time t naught and should go up until time t. Okay. All right. With that fixed, we can get back to it. Okay? So let's just take a look at this integral over here. And applying our second informal integral rule, or excuse me, actually this one over here, what we're going to find is that this integral just kind of picks out the value at time t naught. Okay? So this is equal to c of t, phi of t comma t naught, b at time t naught, times ej, plus d at time t, delta t naught at time t. Okay? Oops, I'm missing an ej. My gosh. All right. Now, if I go ahead and I take coordinate I of this, we'll end up with kind of the following formula. Okay? Let me go ahead and state this formula in the form of a definition. So definition, which is going to be the continuous time, linear time varying impulse response map. So I'll say consider the continuous time, linear time varying system representation, which is A, B, C, and D. The impulse response map, H, is a map on R cross R, defined as follows. So H of T comma T naught is defined as C of T, phi of T, T naught, B of T naught, plus D of T times the shifted delta, delta T naught. And this happens when T is greater than or equal to T naught. All right? And then we're just going to define it to be 0 due to causality, right? If T is less than 0, T naught. And remember, this was because if we're saying our initial state is 0 and we're not applying any input before 0, then our system response should be 0, right? Okay. So notice this formula directly motivates this formula over here. Okay. So I just want to emphasize real quick, mark, for non-zero d of t, this is not a formula we can, I'll put in quotes, calculate like a traditional map. Okay? And this is due to the presence of this Dirac delta. Okay? So due to the Dirac delta. All right? So we should only really be using this in the context of things like integration and convolution. All right? So these are contexts in which we actually understand what this delta is doing. Okay? So should use with integration / convolution. Okay? Because with those two operations, we kind of know in a much more precise way how we should be making use of this delta. Okay, fantastic. So just as a final, couple of results to do with this continuous time impulse response, what we'll do is we'll show that we can almost, you'll see what I mean by almost in just a sec, we can almost write the zero state response of the system to any sufficiently regular input using this linear time varying impulse response map. Okay, so let me go ahead and state a theorem. It says how we can do that. So what this theorem says is impulse response of linear time varying system. So I'll say consider a linear time varying or continuous time linear time varying system with impulse response map H, right? And this takes in two arguments, right? T and T naught. Okay? So I'll say for any signal U, which is piecewise continuous from R to Rm, and any time T and R at which all of our system data is continuous, right? A, B, C, D, and your input U are continuous, then we write the following. Rho of T, T naught, 0, U equals integral from T naught to T, H of T comma tau, U of tau, D tau. Okay? Now, if you want to go ahead and verify that this thing follows the same rule of just translating sum to integral as we go from discrete to continuous time, you can. All right? Notice that this formula looks almost identical to the discrete time case, other than the presence of this integral instead of a sum. Okay. So again, the basic proof of this is you use the representation theorem, but now in continuous time. All right? Which states that U of T equals delta star U of T. All right, and you could do a couple manipulations with there to kind of get yourself to this stage over here. All right, so I'll leave the details to you if you want to try it out. Otherwise, there's a more detailed proof sketch in the notes. Okay, so I just want to highlight real quick remark y continuity. All right, so above, notice that we've said this needs to happen at a point where our problem data is continuous, okay? And the reason for this is that integrals ignore sets of measure 0. Okay, so basically what's going to happen is, if we take our input signal, and let's say it has a jump discontinuity at a single point in time, the integral is going to be pretty much entirely agnostic to that point, right? Integrals can't really measure values that change just on single point sets, right? So that'll entirely disappear from the right-hand side, okay? So what we're doing by, kind of asking that these conditions only holds at points where our problem data is continuous, we're kind of avoiding these problems where we end up with sort of funny behavior on sets of measures 0, okay? So this just makes sure that this is going to be well posed and we won't need to worry about this measure 0 problem. Okay. So just like the discrete time case, I'm going to finish things up by specializing to the time invariant case, all right? So definition, continuous time LTI, impulse response map. So I'll say, consider a continuous time LTI system with impulse response map H, which takes in 2 arguments, right? This is on R cross R. All right. So just like before, we define the LTI impulse response map as just H of t comma 0, right? So it's a single input map, H of t, which is just defined as H of t comma 0, okay? We do the same thing that we did in the discrete time case where now we have only a single input function, okay? All right, so a quick corollary of what we had above is that for a linear time invariant system representation, this guy is going to be computed C times x by t times b plus d, and this is in the case where t is greater than or equal to t naught, and this is equal to 0 in the case where t is less than t naught. All right? Now, another corollary of what we kind of derived above is that for signal u and pc of r greater than or equal to 0, rm, for all t in r where u is continuous, we'll have that the 0 state response will be able to be computed via convolution of this LTI impulse response and the input signal, okay? So we have rho of t 0, 0, u is equal to the convolution h star u evaluated at time t, okay? So this gives us our convolution formula in continuous time. And again, this just follows from a combination of these different definitions and this impulse response property up here. Okay, fantastic. I actually just realized I just made a small typo over here. So it should be 0, 0, and then I'm missing a delta. Okay, now we're good to go. All right, fantastic. So this pretty much puts a cap on our study of impulse response, right? So in summary, we kind of showed that by using these convolutions and these impulse response maps, we can get much nicer formulas for the I/O behavior of our system, okay? And this is nice, but we can actually go even further, all right? And the way that we go even further in our simplification of studying I/O systems is by using transforms, all right? So this brings me to my third and final point of the lecture, all right? So let me just kind of quickly motivate transforms. And just to clarify, by transform here, I mean things like Laplace and Z transforms, okay? So our current issue is we have convolutions describe your I/O behavior. But these convolutions are still kind of somewhat complicated. right? Like the formulas for impulse response, they're certainly much simpler than what we had before, but they're still reasonably complicated formulas, right? As are the formulas for convolution, right? We have like an infinite integral and an infinite sum. And these things are kind of tough to work with, right? So let's kind of lay out like an ideal wish list, right? Things that we wish we were able to do with our systems, right? So our kind of wish lists for how we wish we could perform analysis, all right? So how we wish we could perform analysis, all right? And I'll just focus on the continuous time case here for the sake of brevity. All right. Well, first off, what we might want is that state equations become algebraic equations. Okay? So, state equations are often specified in terms of like differential equations or recurrence relations, right? Which are kind of complicated objects. So if we could just simplify them to kind of a nice, simple, easy algebraic equation, perhaps we could really save ourselves a lot of trouble. Okay? So that would be great to have, right? What else? Well, what we'd also like is that convolutions should be easy to compute. Okay? So currently we have these big infinite sum and infinite integral formulas. It would be great if we could really simplify that down somehow. Okay? All right. So 3, this is kind of looking a little bit further down the line in the course, but it's still important to state now. It should be easy to study the long-term behavior. Okay, so just kind of by looking at some basic properties of our system, we should really be able to easily figure out what the system is going to do in the long term, right? Whether it's going to blow up or kind of converge to something along those lines. Okay, and finally, we should be able to get a simple interpretation, right? We should be able to look at some information about our system, and without having to do any further computations, we can kind of, immediately figure out by inspection what's going on, what the behavior of our system is. Okay? So what we want to figure out how to do is how we can transform our system into something that satisfies these 4 properties. All right? And the key insight is that we can actually transform the objects of our system into the complex plane. Okay? So by translating our currently real objects into new objects in the complex plane, we'll find that we can actually meet all 4 of these specifications. Okay? So I'm just going to very briefly talk about one way we could do this, which is using something called the Laplace transform. Okay? So again, I'm going to be extremely brief and, just give like a lightning overview of the properties and definition of the Laplace transform. Okay? So let me state its definition. We're going to focus on the one-sided Laplace transform. Okay, so here's what I'm going to say. So I'll say consider a function f, which is piecewise continuous, from R into R m by n, let's say. Okay? So the one-sided Laplace transform of f is the function f hat, which is now on a subset omega of the complex plane, and it maps into Cm by n. And this function is defined f hat at any value s, where s represents a complex variable, is equal to L of f of s, which represents the Laplace transform, which is equal to the integral from 0 from the left. Okay, so we're taking the limit, coming in from the left, approaching 0, up until infinity, of e to the minus st f of t dt. Okay? Now I'm going to define this region delta over here is going to be the region of S and C, where the integral converges absolutely. Okay, so if I take the magnitude of everything in the integral, it should be finite, right? And again, this is a subset of C. Okay, so what's going on here? Well, I have a couple of different remarks that I want to make, right? And remark one is that f hat is entirely a function of S, right? T is gone once we did this, right? We completely integrated out T, okay? So what we'll do is we'll often refer to S as the frequency variable, all right? And we will refer to C as the frequency domain, okay? So when we take, some signal, which is a function on R, and we take its Laplace transform, we say that we're taking that signal from the time domain to the frequency domain, okay? So time domain, we apply our Laplace transform. Where we land up is the frequency domain, okay? And just to provide some very basic high-level motivation for why S is called a frequency variable, if we look at this formula over here where we have e to the minus st, this is a complex exponential, right? If you go ahead and you compute this complex exponent, it's actually defined in terms of sines and cosines, right? And you could show that the frequency of those sines and cosines depends on this value s, okay? So that gives you some kind of very basic idea of why S is associated with frequency. We'll talk about a more fundamental relationship between S and frequency later in the course when we talk about frequency response, okay? All right, so those are a couple of basic remarks that I have about this one-sided Laplace transform, right? It takes us from a function of time, f, to a function of frequency, f hat, all right? So just by convention, if we're given this kind of lowercase letter for our signal, we write its Laplace transform as an uppercase letter with a hat, okay? All right, so let me outline some very basic transform properties. Okay, so first I'm going to talk about the Laplace transform of two really important signals. Okay, so first, if we take the Laplace transform of a Dirac delta, we evaluate that at any s and c, then it's automatically equal to 1. Okay, so the Laplace transform of delta is just 1. Super simple. Okay, now second, if we take the Laplace transform of the step function, right, which is 0 for t less than 0 and 1 for t greater than or equal to 0, this guy is equal to 1 over s. Okay, so just to clarify, this is the function that jumps up at time t equals 0 to a value of 1. Okay? Now, third, what we'll have is a nice property about differentiation in the Laplace transform. Okay? So if we take the transform of a differentiable function f, we take the transform of its derivative, L of d dt of f of t is equal to s times the transform of f, so s times f hat of s, minus the limit as we approach 0 from the left of f, okay? So differentiation becomes super simple in this in this frequency domain, all right? Now finally, for our last simple property, okay, we'll have linearity, all right? And this is L of alpha f plus beta g is equal to alpha L of f plus beta L of g. Okay, and this is just a consequence of it being from an integral. Okay, so those are our 4 basic properties. Now the really fundamental property, which I'll state now, is one about convolution. Okay, so this is really what makes the Laplace transform valuable to us. And what the convolution property is that convolution of signals becomes multiplication under the Laplace transform. Okay, so we go from this super complicated operation of convolution, which involves all these infinite integrals, and we just go down to multiplication. Okay, that's super easy. So L of g star u, let me say I'm taking the convolution of these two signals, is equal to, if I evaluate this as s, this is equal to g hat of s multiplied by u hat of s. Okay, so convolution becomes multiplication. All right. Now, let me just define a couple more relevant quantities for studying systems in the frequency domain. Okay? Now, one really important property is something called the transfer function. All right? So earlier, what we did is we had said that this impulse response of our system, it really enables us to kind of compute the system response to any sort of input that's out there. Okay? So since we have that, the response of the system is equal to a convolution of impulse response and input, and convolution becomes super simple in the frequency domain, then it should kind of seem fairly natural that the impulse response, or its Laplace transform, should be a really fundamental object in the frequency domain. Okay? So this is called the transfer function of the system. So definition, which is the transfer function. So I'll say, consider a continuous time LTI system with impulse response map H, right? And this is the LTI impulse response map. Okay? So the transfer function of the system is defined as follows. So it's defined h hat of s equals the Laplace transform of h. Okay? So we just take the Laplace transform of our impulse response map. We end up with this thing called the transfer function. Okay? So by combining this property with the convolution property, the transfer function can really tell us a whole lot about how our system's going to behave. All right? So let me just state one final proposition, and then we'll end the lecture. So proposition, this is the transfer function of a continuous time LTI system. All right, so I'll say, consider a system representation A, B, C, D. Okay, this is an LTI continuous time system representation. So the transfer function of the system is computed. H hat of S is equal to C times Si minus A inverse B plus D. Okay? Where this map is defined, where this inverse Si minus A inverse is defined. Again, I'll talk about this a little bit more in the optional video on the Laplace transform. So let me just give you a quick derivation of that. So what I'll do is I'll start with my state equation and my output equation, right? A times x of t plus b times u of t, y of t equals cx of t plus du of t. Then I'll take the Laplace transform of both of these from zero initial condition, right? Because we're interested in the zero state response. What I'll find is s x hat of s equals a x hat of s plus b times u hat of s. And since I'm interested in the delta function and the transform of the delta is just 1, right? I'll just end up with a 1 over there. Then I will get y hat of s is equal to c x hat of s plus d, again, times 1. Okay? Now, all that I need to do is just collect the x terms, right? So if I solve for x and then I plug into the second equation, I'll end up with y hat of s is equal to c times si minus a inverse x hat of s plus d. Okay? And that pretty much finishes things up. All right, thanks for watching.